We're finally ready to talk about the Schrodinger equation, although before we get to the equation itself, we have to go back and talk a little bit more about wave functions. Up until now, we've used wave functions to refer to a function or a vector that represents the spin state of a particle. The probability of finding this particle in any particular arbitrary spin state is equal to the magnitude squared of their inner product. And the inner product inside the magnitude squared is called the probability amplitude. We can do the same thing for the position of a particle, though. So, for example, instead of defining a state vector describing the spin of a particle, we can define a state vector describing the position state of the particle. However, we immediately run into a little bit of a problem. For the spin of a particle, it's quantized, which means in any particular basis, it can take one of two values. That means we can write down the state vector as a simple linear combination of those two with corresponding probability amplitudes. But position is not a discrete variable. It's continuous. A particle can exist at any of an infinite number of continuous values of position along any particular axis. So if I wanted to write down my position space state vector the same way I did for spin, I would be writing it for the rest of all eternity, and I would still never finish because I would never run out of terms to write down. Using the tools of linear algebra, it is possible to define this position space state vector rigorously. We're not going to worry about it, though. We are not going to be manipulating the position space state vector itself. But we can follow the same procedure as before to calculate the probability of finding any particular state in a particular value of position, where the x on both sides of this expression essentially represent the x variable, the set of positions along the x-axis. And once again, the inner product inside the magnitude squared is the probability amplitude corresponding to the probability itself. But if you think of this inner products return numbers, complex numbers, right? So the inner product of some random value of position with our position space state vector returns a number. And a different value of position will return a different number in this inner product. In other words, this inner product can be thought of as a function of the variable x. And this is where the notation becomes a bit inconsistent, because we typically just call this function psi of x the wave function. But sometimes we'll call the state vector the wave function as well, just like we often did with spin. So it's a little bit contextual. For our purposes, in the context of position, we are never going to worry about the state vector because it requires more advanced math than we really have under our belt. We are going to stick with the function representation, in which case psi of x is going to be what we refer to as the wave function of our particle's position. And really, generally speaking, the psi here and here don't necessarily have to be different things. Generally speaking, a particle simply only has one state vector, which describes all of its properties, from spin to position and any other property you can think of. And what we've written down as the state vector for spin over here really only represents one piece of a much bigger vector. So we've just picked out two components of a vector that is really much, much, much bigger, and it encodes all the information about the particle's position and other properties as well. And so if we think of psi as the complete state vector of the whole system, then what we're doing here is we're saying, okay, all I care about here is the position piece of the wave function. I'm bringing out only the parts of our wave function that have to do with position over here, and over here I'm bringing out only the parts of the wave function that have to do with spin. The other thing that we need to deal with is that while this quantity over here is in fact the probability of finding the state psi in the state phi, this quantity here is not a probability. Instead, it's a probability density. And technically, the wave function, or what we used to call the probability amplitude, is now a probability density amplitude. We haven't renamed it just for the sake of it. For example, consider the x-axis, and imagine that we have a particle that's confined somewhere between the values of x equals 0 and x equals 1. And imagine that it's equally likely to be found anywhere, like a ball bouncing back and forth. You have no idea where it is. When you open the box and look, you have an equal chance of finding it anywhere in the box. So here's the question. What is the probability of finding a particle at the value of x equals 1/2 exactly? It's actually 0. There are an infinite number of positions that the particle can exist at from 0 to 1. The number of real numbers between 0 to 1 are uncountably infinite. In fact, there are as many real numbers between 0 and 1 as there are between 0 and 2, or 0 and 3, or 0 all the way to infinity. If you've never seen or heard this before, first of all, I encourage you to look it up. If you just search for uncountably infinite or something, I'm sure you'll find dozens of resources. But rule number 1 when dealing with infinite sets is that your intuition is useless and it will almost always only get you into trouble. But since the position 1/2 is simply one of an infinite number of places the particle could be, then the probability of finding it there must be exactly equal to 0. And that's true of any other position. But it's a little useless to say, oh, well, the probability is 0 everywhere. Okay, then what do I do? Well, maybe you'll say, well, if it's 0 everywhere, then it's equally likely to be found anywhere. Great, that's kind of what we set out to do. But let's change it now. Let's say that the particle is twice as likely to be found in the region from 1/2 to 1 than it is in the region from 0 to 1/2. Well, how likely is it to find the particle at the position 3/4? It's still 0. I mean, there are still an infinite number of positions between 1/2 and 1, so even if we ignored the left side entirely, the chances of finding it at exactly 3/4 would still be 0. And so here, the probability of finding the particle at any value of x from 1/2 to 1 is 0, but it's also 0 from 0 to 1/2, but it's twice as likely to be found in the interval from 1/2 to 1 than it is in 0 to 1/2, and so now we have nonsense. It doesn't make sense. If you want to make mathematical sense of talking about the probability of finding something at an exact value of position like this, you need to bring in additional concepts from the field of real analysis. In this case, you need to bring in the concept of a measure, and it becomes kind of complicated. But in physical terms, it doesn't matter, because talking about the probability of finding a particle in an exact value of position is meaningless anyway, because can you compare that to a measurement? Can you go to a lab and say, oh, yeah, that's what I got? No, because we can't measure exact values. There is no way to remove 100% of uncertainty from any measurement. Even if we manage to get around the intrinsic quantum mechanical fuzziness of typical systems, we'll never be able to get past the limitation of our measuring devices themselves. So instead of talking about the probability of finding a particle at a value of x, we instead talk about the probability of finding a particle within a range of values of x. And the probability density tells us the relative probability of finding a particle per unit length as a function of position. So to calculate the total probability, we integrate the probability density over the interval that we're looking for. I want to emphasize that this is really not anything particularly new. This is simply a difference between how we treated spin and how we have to treat position, because of the fact that spin is a discrete quantity with a finite number of values, whereas position has an infinite number of values within a given set of basis vectors. I also want to remind you that this relationship between the wave function and the probability, whether with spin or with position, is a postulate of quantum mechanics. This is not something that we derive. It's something that was hypothesized and subsequently verified over the course of 100 years by this point by experimentation. It's called the Born rule after the physicist who first proposed it, named Max Born. The Born rule also imposes a very strict requirement or restriction on the kinds of functions that can be wave functions. Because if a particle exists and you look for it everywhere, then you must find it, which means the probability of finding the particle between x equals -infinity and infinity has to be equal to 1. It can't be more and it can't be less. Neither of those would make any sense. This is just the normalization condition for wave functions. And we've seen this before with spin as well. The difference is that with spin, the normalization condition required that the sum of all the probability amplitudes have to add up to 1, Whereas here we have an infinite sum of all the probability amplitudes having to add up to 1, because instead of simply having a finite number of possibilities, now we're dealing with infinite possibilities. I should also emphasize that this magnitude squared is still important because the wave function psi of x is, in general, complex valued. But let's take a second to qualitatively analyze how we can interpret a wave function. So first, because I can't graph a complex valued function easily, let's just assume that our wave function only has real values. If this is the wave function of a particle, then the most likely place to find the particle is right here. Remember that the probability density is the magnitude of the wave function squared. So the fact that this is negative doesn't matter. First we take the magnitude so it becomes positive, and then we square it. If I ask where is the second most likely place for the particle to be found, a common answer would be over here, or maybe over here, because the magnitude of the wave function here looks the same as over here. But that's not right. The second most likely position to find the particle in is infinitesimally close to the first most likely position to find the particle, because the magnitude of the wave function here, a little bit off from the actual minimum, is still substantially greater than at either of these peaks. Another useful thing to analyze is where could the particle never be found? If the wave function is equal to 0, then its magnitude squared is equal to 0. And so anywhere the wave function is 0, the particle will never be found. So these two positions, particle will never be found there. No matter how often you look, you'll never find it there. Now, again, because our measurements are imperfect, you might find that the particle is within some small region around that. Very unlikely because the wave function is very close to 0 near these points, but not impossible. And if you perform the measurement enough times, eventually you would even expect to find a particle near one of those 0 points. If we really want to analyze the probability itself, what we should do is we should draw the magnitude squared of our wave function because that is a much more direct representation of what the probability of finding a particle within a region would actually be. And note that I've drawn a new set of axes because I can't plot a function and a function squared on the same set of axes. Really, I mean, these are dimensional quantities. The wave function has units, so I can't put them on the same axis. And just because the wave function has a peak doesn't mean that the wave function's magnitude squared will be bigger, because if you square a small value, it can result in a smaller value. So it really depends on what the actual values of these things are, what the result will look like. Here I've drawn an arbitrary function that looks qualitatively correct for what this function would look like squared, depending on what values you might assign to it. Also bear in mind that there is no upper limit to what the value of the wave function can be. The wave function can have a really, really, really enormous value. It's not restricted to being less than one unit or whatever. It's only the integral that has that restriction. So you can have a wave function with a very, 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 very high value over a very small region, such that the integral, the area under that large value over a small range, is equal to 1. Based on the way that I drew this probability density, it's clear that the particle is much more likely to be found in this region over here, or rather I should say along this interval over here, because the area under the curve of the integral is very large over here. It's also more likely to be found between the second and third 0 points than it is to be found between the first and second 0 points, because qualitatively at least, I think it's clear that the area under here is a little bit more than the area here. So we can analyze the relative probabilities of finding a particle simply based on the shape of the wave function, and even more straightforwardly, based on the shape of the magnitude of the wave function squared. Being able to qualitatively analyze a wave function isn't all that helpful if we've got no idea where they come from, though. And that's where the Schrodinger equation comes in. But the Schrodinger equation wasn't actually really derived. Erwin Schrodinger wasn't just the first person to solve a math problem and come up with this equation, but it was instead more of a hypothesis. In particular, he was dissatisfied with the quantization condition in the Bohr model of the hydrogen atom. While the quantization of the energy levels in the hydrogen atom were well established and he didn't deny them, he wasn't satisfied with the proofs or assumptions that went into justifying them. They were contrived and kind of hand-wavy, and they didn't always really work, and so it was a little bit problematic. Schrodinger was convinced that this quantization should arise naturally from some sort of eigenvalue condition. After all, eigenvalue equations very frequently result in discrete solutions, which is exactly what we were seeing in nature. And since the quantization observed regarding the hydrogen atom was of its energy levels, he decided to start with conservation of energy. Here, E represents the total energy of the system, K represents the kinetic energy of the system, and V represents the potential energy of the system. The total energy of a system goes by another name in physics. It's called the Hamiltonian, after a very prominent mathematician named Hamilton. And while it might seem a little bit pointless to have another name for total energy of the system, there's actually some value to it. First of all, it plays an important role in Hamiltonian mechanics, which is another way of mathematically describing the mechanics of a system. But also, if you think back to what we know about quantum mechanics, observable properties of systems are eigenvalues of linear operators that we can apply to the quantum state corresponding to that system. And so generally, we think of energy as the eigenvalue of the Hamiltonian operator, although in classical mechanics, there's not a really big difference between the two. But Schrodinger already knew that measurable quantities in quantum mechanics corresponded to linear operators, and so he set out to try to figure out a way to express these components of the energy of a system in terms of linear operators. And since Schrodinger knew that particles behaved like waves and that describing them correctly required using complex numbers, he started by writing down the simplest complex wave that you can. He also knew from Max Planck and Einstein 20 some odd years earlier that the energy of a quantum wave could be expressed as hf, or h bar omega, and he used the de Broglie wavelength to say that the momentum of this particle is equal to h over lambda, or h bar times k. Incidentally, it might be a little bit more obvious now why we introduced the reduced Planck's constant. It makes things a little bit cleaner. This prompted Schrodinger to re-express his conservation of energy expression in terms of momentum instead of kinetic energy. His next step was to look for the momentum operator and the energy or Hamiltonian operator, whose eigenvalues are the momentum and the energy of the wave that he wrote down, respectively. By plugging in this wave function into these expressions, into these eigenvalue equations, and making use of the relationship between E, omega, and P and K, Schrodinger showed that the momentum operator could be written as minus I h bar times d dx, and that the Hamiltonian or energy operator can be written as I h bar times d dt. Technically, both of these should be partial derivatives, not total derivatives. If you don't know what a partial derivative is, don't worry about it. If you do know what it is, now you know. Since we're going to restrict ourselves to one-dimensional equilibrium problems, it's not going to matter whether we use partial or total derivatives, so I'm just going to keep it simple. This allowed Schrodinger to rewrite his conservation of energy statement in terms of the corresponding energy and momentum operators, where V is just a function of position and time. It's the potential energy. It doesn't really depend on the properties of the particle so much as it depends on the position of the particle in some external field. And plugging in the forms of the operators that we just established, we can rewrite the equation in terms of derivatives with respect to time and position. Right now, this is just an operator equation. We haven't operated our operators on anything yet. There's nothing stopping us from doing that, though. We can simply operate the left and right-hand side of this equation onto our wave function. And this is the complete time-dependent one-dimensional Schrodinger equation. Note that there are only two inputs to this expression, to this equation. One is the potential that the particle is exposed to. So essentially this encodes all the information about the external forces and influence on our particle. And the other is the mass of the particle. Nothing else shows up. Worrying about how the wave function changes over time is complicated and messy, and we're not going to worry about it. We're going to stick to equilibrium systems. If a system is in equilibrium, it means that its energy is constant. And since this left-hand side of our equation can be written as the Hamiltonian operator acting on our wave function, well, the Hamiltonian is the energy operator, and so the Hamiltonian on our wave function should just give us the energy times the wave function. And if our system is in equilibrium, it implies that our potential is not changing over time. This is the time-independent one-dimensional Schrodinger equation. It's a lot simpler to deal with since all we have is this 1 second derivative term, and we do have to worry about this guy over here, but this left-hand side becomes dramatically simpler. Both of these equations are linear differential equations, which essentially just means that both sides are simply a linear operator acting on a function. That gives certain properties to the solutions of these equations. We're going to focus on the time-independent one. In particular, if psi1 is a solution to the Schrodinger equation, then any complex number times psi1 is also a solution to the Schrodinger equation. Secondly, if psi2 is also a solution to the Schrodinger equation, so more than one solution, then the sum of psi1 and psi2 is also a solution. But bear in mind that the left side of our equation is the Hamiltonian acting on our wave function. So if we plug in psi1 plus psi2 as our solution, we're applying the energy operator to this sum of states. And since the Hamiltonian is a linear operator, we can write it as h psi1 plus h psi2. Now the simplest solutions to this equation are the eigenstates of the Hamiltonian operator. Any wave function that is an eigenfunction of this operator is going to be a solution to this expression. And so if psi1 and psi2 are eigenfunctions of our Hamiltonian, then the Hamiltonian acting on them is simply equal to the eigenvalue times the function, which in this case would be their corresponding energies. But here's the rub. What is the energy of this wave function, psi1 plus psi2? It's not E1, and it's not E2, and it's not E1 plus E2. It's a linear combination of E1 and E2. This wave function represents a state in a superposition of energy. Energy, it turns out, is subject to the same strange quantum behavior as we already established with spin. If you were to measure the energy of this particular system, it would have a probability governed by the component of the wave function psi1 to collapse into a state with an energy of E1. And it would have a separate probability given determined by psi2 to collapse into a state with an energy E2. This sounds problematic. It sounds like it would violate conservation of energy. But if you think about it, this is again no different from spin. Spin is a measure of angular momentum. Angular momentum is also conserved, and yet it could exist in a superposition just fine. Though there is, of course, a great deal of nuance and new ideas to get used to. Now let's go back to this first point. If psi1 is a solution, then any complex number times psi1 is also a solution. But if we bring back the Born rule, we'll find that this seems to lead to some problems. If we use the Born rule to write down our normalization condition for our wave function, and if our initial wave function psi1 is in fact normalized, then unless c is a complex number with a magnitude of 1, then c times psi1 will not be normalized. This tells us that the Schrodinger equation isn't the whole story. The Schrodinger equation doesn't tell us the wave function of a system. The Schrodinger tells us the wave function of a system up to some normalization constant. So once we've solved the Schrodinger equation to find the values of psi that work, then we have to plug that into our normalization condition from the Born rule, find out what we get, And if it's not equal to 1, we have to multiply our wave function by some complex number so that it is equal to 1. We have to normalize the wave function. So the Schrodinger equation gives us the qualitative behavior of the wave function, but it doesn't give us the correct normalization in general. We have to do that by hand ourselves with this additional extra step. So let's do a quick example. Imagine we've already gone and solved the Schrodinger equation for a particular potential energy function. And we got that the wave function is equal to a number, an arbitrary constant, let's call it n times x, between x equals 0 and 1, and it's 0 everywhere else. We want to find the value of n, so what we do is we normalize our wave function. We plug our wave function into the normalization condition, we demand that it be equal to 1, and we solve for the variable, or the unknown, n. And since in this case our wave function is defined piecewise, which, by the way, if your potential is piecewise, your wave function will also have to be piecewise. And in this case, over the intervals where the wave function is 0, the probability is also 0. And over the interval from 0 to 1, x is always a positive number anyways, and so we can drop the absolute value on the x. Now we can integrate this polynomial integral, no problem, and we end up with a condition for the value of n, or rather the value of the magnitude of n. And since n is an overall phase of our wave function, it doesn't really matter whether we make it real or imaginary or complex valued as long as it has the appropriate magnitude. There are some occasions where that's not necessarily true. There are other conditions that restrict the phase of n, but in this case, it's nice and simple. We're going to stop here, but one thing that I do want to elaborate on is the way that we came up with the Schrodinger equation. I want to emphasize again that we didn't derive it, we motivated it. In fact, there are some funky things went on over here. In particular, this particular wave function is called a plane wave solution, and it only really works if v is equal to 0. It's the free solution, so it's just a wave propagating forever through all space and over all time. And we use that to motivate the form of the momentum and Hamiltonian operators, but we didn't justify that it works in scenarios other than the one that we started with here. This whole process, and while Schrodinger's actual process here was a little bit more rigorous than what we did here, but really not very much more, this was really just kind of a guess. He was playing around. This was in the middle of the 1920s when everyone was still very confused about what was going on, and Schrodinger was just futzing around mathematically, trying to come up with some kind of eigenvalue equation that could possibly result in the quantization conditions that we see from the hydrogen atom. And we're still use the Schrodinger equation because it turned out that his futzing around was quite inspired, and the Schrodinger equation seems to work. It is the equation that defines non-relativistic quantum mechanics. Schrodinger set out to come up with an eigenvalue equation that could be used to justify the quantization condition postulated by Bohr for his model of the hydrogen atom, and he was successful. I don't remember if it was Schrodinger who showed it or if it was somebody else, but this equation can in fact be used to derive the quantization condition for the hydrogen atom to within less than 1% of a difference from measured values. And by adding on some bits and pieces to account for relativistic effects and so on, it can be made even more precise. Something I want to drive home. The Schrodinger equation, the backbone of non-relativistic quantum mechanics, is not something that is proven. It is something that is guessed. And we've seen that with special relativity as well. Ultimately, all of our understanding of physics in the natural world is based on some set of fundamental assumptions about the world. And those assumptions can't be derived from anything else. They're empirical in nature. We make observations, we futz around, we make guesses, we come up with hypotheses, and we test them. And ultimately, some of those guesses that we made stuck. we try to test them, we try to disprove them over and over again, and we can't. Every time we try, we just end up showing that, oh, it worked again. That is the process of science. Sometimes we start from things that we know, and we can mathematically turn that into some new piece of information. We can sort of triangulate from information that we know into some new piece of information. But other times, we simply come up with new empirical observations about the world. The Schrodinger equation is one of them. E equals hf is another one of them. P equals h over lambda applying to all matter and not just light is another.